Okay, continuing on with what we talked about yesterday, we'll finish up our notes today on confidence intervals. But we'll have 3 different more days with respect to confidence intervals. Looking for a quiz next Friday on this. And once again, this is material that I would guess, I'd venture to say this is probably the easiest of the material that we go through all throughout the year. When you're talking about parameters, once again, you talked about population. We're trying to estimate a population, just like the presidential elections, or any type of elections, they try to get a good guesstimate in regards to what they feel the population is going to give you in regards to voting. So that's a parameter we're trying to estimate. We took a look at a dog problem yesterday. $6,400 to raise an average sized dog, medium sized dog to age 11. $6,400 and how that could happen. The best point estimate for our point estimates, a specific numerical estimate of the parameter. The best one is going to be just your sample mean. If you can find the sample mean, that's a good basis for a point estimate. Talked about estimators, 3 good properties of an estimator, and you will have to be able to give me what's a couple characteristics of a good estimator. Should have those. Let me work through a problem that dealt with the average age of a car and what percent probability there is in regards to it being between 90 months and 100 months old, which is an average car. It's a 92% probability that you're going to have a car that's going to be between 90 and 100 months. Also, we can restate it as 92% confident that the mean will lie in between those 90 and 100 months. Then we looked at interval estimate, confidence interval, and this interval estimate, these two are very similar to each other. Very similar to each other. We're looking at an interval. Okay, we'll be taking a sample with size n. We'll calculate the interval using a z-score to illustrate a confidence level that the population mean will be somewhere between this value and this value. Most confidence levels are 90, 95, or 99%. The population average of salary for teachers in Ohio is $41,000 a year with a standard deviation of 1,500. What's the upper bound and lower bound for that salary to encompass 9% of the salaries? Okay, 90% of the salaries. Well, if you remember what we did a bell-shaped curve. Finding these boundary values, and we want the middle 90%, the middle 90% of the salaries in the state of Ohio. So we put 90% there on each side of our 0, each one of these percents. This is the same notes we had yesterday. On each side of the 0, if we have 90% there, tell Ramsar, what are we going to have percent-wise on each side of the 0? 45. 45. And we translated this into an area. A 0.4500. We went to our z-score, or our z-table, and we looked up in our z-table, the value in our Z table, in the middle body of our Z table, we looked at 0.4500. And what we came down to before was this was in between two specific values. And those two values were 1.64 and 1.65 on the Z-score. I said you could use either. Well, I'm going to be more specific now. I'm going to say we're going to use 1.65. And once again, that's just coming from our Z table. We have a mean of 41,000. We have a standard deviation of 1,500. And we can calculate these values by using mu plus our standard deviation times our Z-score. So we can come up with two values. Go ahead and come up with the two values. Bless you. Square it. And once again, we're just doing what we just did. There's nothing new here. Sarah, our top boundary value would be what? 470 what? Our bottom value? What's our bottom value going to be, Emily? 38,545. So we're 90% confident that if we pick somebody at random, it's going to be somewhere between these two values. Okay, because 90% of the salaries are going to lie between 38,525 and 42,475. So 90% of the salaries lie between those two values.
Luckily, I haven't seen his dad in a while. Luckily, I haven't been near Chad in a while. I wondered if someone at work got tested and tested positive, so he had to test. I'll tell you that if we do, it's going to be very little.
Now, if we remember our sigma x bar is equal to sigma divided by the square root of n. Okay, this is what we worked on in the last chapter with the central limit theorem. So what we're able to do with this is do a substitution and transform our base equation up here into this base equation when dealing with a sample mean. Our sample mean and a sigma and the square root of n. And basically what this comes down to is how we found our z-score with the central limit theorem is x bar minus mu divided by standard deviation divided by square root of n. If I multiply both sides by sigma times divided by square root of n times z, and then add our x bar to that, this is what we transform into. Which now allows us to go into the next type of problem. If I have a sample of 40 teachers, are chosen from the population of all Ohio teachers. Their mean salary was $41,000 with a population standard deviation of 1,500. It's the exact same thing. Find a confidence interval for a confidence level of 90%. When I say a confidence interval for a confidence level of 90%, what we are trying to determine is boundary values we're trying to find boundary values that will encompass %90 of the salaries or of the means. Or 90% of the salaries. Our boundary values or a bell-shaped curve still looks the same. We still look at 90%, 45, and a z-score then that will come down to negative 1.65 and a positive 1.65. The bell-shaped curve looks exactly the same. The z-scores are going to be exactly the same. What will change is how we calculate these boundary values. Our boundary values can be calculated by x bar minus our z-score times our standard deviation divided by the square root of n. I'm sorry, that should be a plus. So our boundary values, how we find these two boundary values, how we calculate them just changes a little bit. Rather than just multiplying our z-score times our z-value times our standard deviation, we now have our z value times the standard deviation divided by square root of n. So now we have our 41,000 plus a negative 1.65 times our standard deviation divided by the square root of 40. And then 41,000 plus a 1.65, 1,500 divided by square root of 40. And it turns right into a clicky-clack exercise at this point. You can click that straight through the calculator. You can type in 41,000 plus a negative 1.65 times 1,500 divided by square root of 40. And then 41,000 plus 1.65 times 1,500 times square root of 40. You can just type it in and hit enter. You don't have to break it into pieces parts. Our two values. Okay, when we had negative 1.65 times 1,500 divided by the square root of 40, what do we get with the first value, Brooke?
40,608.67.
And our bottom value?
41,391.33.
So this will encompass 90% of the salaries. But what the second meaning to this will be is we're going to be 90% confident the population mean is between 40,608 0.67 and 41,391.33. So we're 90% confident that the mean salary, the population salary for the teachers in the state of Ohio between those two values. Why? Because 90% of the data is going to lie between those two values. If 90% of the data lies between them, we're 90% confident that the population mean is going to be in that value also. Most confidence intervals are going to be either 90, 95, or 99%. An alpha value can be calculated also. It's a level or amount in the two tails. Is basically the percent that you're not confident. It's your percent not confident. And how we can calculate the alpha value? Is 1 minus our confidence interval. 90% of the scores lie between these two values. That means 10% don't lie between those two values. That's your alpha value. Your alpha value is your percent not confident. If you're 99% confident, that means I'm 1% not confident. This here is your population mean. Your population mean will be in between x bar minus your z value for the confidence interval times your standard deviation divided by square root of n, and x bar plus the z value times the standard deviation divided by the square root of n. So ultimately, you want to predict the population mean. And we can predict range of values that you're going to be in between. And this is what we will be calculating. Now, to do a bell-shaped curve each and every time. To do a bell-shaped curve, then sit there and go here, 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 and then deal with, okay, this is 95% is here, so this is 47.5%, 47.5%, 0.4750, 0.4750. And then go to a z table and find this value from a z table. And be able to determine a z value each and every time is a lot of time-consuming energy. For our homework tonight, what you'll want to use is this table right here. if I have a 90% confidence interval, that means I'm 10% not confident. That means my z-value I'm going to use is 1.65. If I have a 95% confidence interval, the z-value I'm going to use is 1.96. And if I have a 99% confidence interval, my z-value is 2.58. You do not need to memorize these. You can pull these off the table. You do not have to do a bell-shaped curve and find a z-value each and every time. You can go to this table and use these values. You will have a table that you'll use for the next test. You'll be able to pull these z-values off of it. You will not have to memorize them. Your maximum error, not to be confused with your maximum effort. Your maximum error is your difference between the population mean and the maximum distance to your confidence interval. You gotta talk nicely to it, Cameron. We just gotta talk nicely to it. If you start getting, yeah, that's exactly right. You start getting all any stuff about it, it's not gonna happen. There you go. And how this maximum error can be calculated is your z standard deviation divided by square root of n. How do we find our confidence interval? Is this. This value right here is your maximum error. This maximum error is just x bar minus the maximum error and x bar plus the maximum error. Because once again, the best point or the best point estimate to a population mean is just a sample mean. And that's what this is saying. Then we have to add or subtract that maximum error. If the population standard deviation is not known, use the sample standard deviation. Because you can calculate the sample mean, you can calculate the sample standard deviation also. Maybe you don't know the population. That's fine. Get a number down there. So what this turns into this confidence interval just turns into and you could just most books will put that alpha divided by 2. I put CI there, confidence interval. So basically, you take out sigma and you put in S. If you want to be more confident the population mean lies within the interval, you must be willing to trade off a bigger confidence interval. If you want to widen the range to make sure you're confident, that's fine. But your range of values will be bigger. The bigger the confidence interval, the bigger the range of values. To find a confidence interval, the sample size must be large enough to calculate, or we will use above 30 for right now. That is, n has to be bigger than 30. Get a lot of theory behind this. When we get into problems, you'll see the difficulty level is not very high. If you remember x bar minus plus or minus z standard deviation divided by square root of n, you'll be able to do all these problems. But once again, we try to get above 30, but if we look at a maximum error, if we're given a maximum error, a minimum sample size for a maximum error, we can find a sample size with this. We'll get into a few problems like that eventually. A survey of individuals who passed the 7 exams and obtained the rank of a fellow in the actuary field find an average salary of $150,000. Applied math actuaries, they make buku bucks. If you're good at it, they make big bucks. Why? Because big time businesses and corporations want to have people there that are going to be able to predict if they can make a huge profit. It's important that businesses understand, if I buy this company or do this, promote this product, I can get more money. Survey finds the average salary, $150,000. The standard deviation of 35 fellows was 15,000. Constructed 90% confidence interval for all the fellows, the population. So what we have here is we have an X bar of $150,000. We have a standard deviation of $15,000. We have a sample size of 35. And we want a confidence interval of 90%. Looking at our table, if I have a 90% confidence interval, what is the z value that corresponds with a 90% confidence interval? Rich? 1.65. You know what, let's do this one, that's fine. So I want to construct a confidence interval. So we have for the population, So I have x bar minus our z value times the standard deviation divided by the square root of n, and then x bar plus the z value standard deviation divided by the square root of n. Putting in numbers, $150,000 minus 1.65. Standard deviation of 15,000 divided by square root of 35. And then we just change it into a plus. Now it turns into a clickety-clack exercise. You find two values. 150,000 minus 1.65 times 1,500, or 15,000 divided by square root of 35. Hit enter. And then type in 150,000 plus 1.65 times 15,000 divided by square root of 35, and hit enter. And we get two values. Check your hands with somebody around you. Ellen, what's your two values? 145,000, Good with those values? If you're off by a penny, don't worry about it. And then we have to write a statement at the very end. We are 90% confident the population mean is between 145, 816.5, and 154, 883, and 50 cents. Don't think 50 cents really matters when you're dealing with $154,000 a year. In your homework, you have some confidence interval problems to do. I'm going to tell you in each one of these homework problems, I'm asking you to find a 90, 95, and 99% confidence interval. What I want you to do is pick two in each of them, and just do two. Just pick two. Don't pick the same two each time. Do 90, 95, then 95, 99, then 90, 99. Pick two of them. And find a confidence interval. It will be the same process each and every time. Use your table for your z values. It will be the exact same equation every time. when you're going through the problems. Questions?